In regards to equilibrium, so far we have talked about defining equilibrium as being a point where our rates become equal, the forward and reverse reaction rates, our concentrations become constant. We've talked about that resulting in a particular equilibrium mixture that's described by our equilibrium constant K. We've talked about using the size of K, so whether it's small, intermediate, or large, to determine what that equilibrium mixture should look like. And we talked about using the reaction quotient Q to determine if our reaction has reached equilibrium. The final thing we're going to be taking a look at is something called the Chatlier's principle. So remember that once a reaction reaches equilibrium, our concentrations no longer change. For a manufacturer of chemicals or pharmaceuticals wanting to obtain maximum yield and maximum money, this can pose a problem. There's still unused reactant wasted, and the maximum amount of product hasn't been formed. However, there are ways in which we can manipulate an equilibrium, forcing it to continue in either the forward or the reverse direction. We can disturb the initial equilibrium by applying what we call a stress that in turn causes that equilibrium to shift. When we talk about an equilibrium shifting, that is just a temporary change in rates. That means one of our rates is going to speed up for a period of time until we reestablish a new equilibrium. And this is Le Chatelier's principle. Le Chatelier's principle tells us that our equilibrium will shift to relieve an applied stress. Now, these stresses that can change an equilibrium are going to include changes in concentration, changes in pressure or volume, or changes in temperature. So first thing we'll take a look at is changes in concentration. So concentration can be changed by adding or removing either a reactant or product. And in particular, it is one that is either aqueous or gas. Remember that solid and liquid do not influence our K value, and therefore they do not impact our equilibrium. Changes in solid and liquid will not cause a shift in our equilibrium. Changing concentrations of aqueous or gas substances will alter our Q, or alter our ratios, which controls the direction in which the reaction will proceed or shift in order to re-establish equilibrium. So we have a reaction in which we've reached equilibrium. If we add more reactant, we now have a scenario where we have excess reactants. We need those reactants to go down in order to reestablish our equilibrium ratio. So what's going to happen is our reaction will shift to remove that added reactant, resulting in the formation of more product until a new equilibrium is established. The equilibrium shifts right towards the products. The reaction proceeds in the forward direction. Now, if we were to add more product, the reaction will shift to remove that added product, resulting in the formation of more reactants until a new equilibrium is established. The equilibrium shifts left towards the reactants. The reaction proceeds in the reverse direction. So if we're adding something, whether it's a reactant or product, the equilibrium shifts away from what we added to use it up. So if we add reactant, we shift away towards the products so that we form more product, we use up reactant. Add more reactant, we shift, or add more product, we shift away from the products toward the reactant. So we're going to use product, we're going to form more reactant. So if I were to just look at a generic reaction, I've got A plus B produces C. So if we were to add more A or B, so we're adding more reactant. We said our equilibrium is going to shift away from that reactant so that we can use it. It's going to shift forward towards the products. So that means at that point in time, we're going to get a temporary speed up in that forward rate so that we can form more product, we can use reactant, we can reestablish our equilibrium. So what happens during that time is the concentrations of A and B are going to decrease. The concentration of C will increase. If we were to add C, and this is when we're at equilibrium. If we were to add C, that is adding product. We're going to shift away from the side we added things to, so it shifts towards the reactants. So we're going to get a temporary change in rate towards that reverse direction. As a result, concentrations of A and B would increase and C would decrease. So we said we can use these to our advantage. So if we have a reaction and our goal is to create those products, what we can do is we can let our reaction reach equilibrium and then we can add more reactant. That shifts it forward and we get more product. So a very common way to perform a chemical reaction might be to slowly add reactants over time so that we can use up as much reactant as possible, constantly shifting our equilibrium in the forward direction. Now, the scenario where we're adding product, that might be a situation where maybe we're dealing with the decomposition of a chemical and we don't want it to decompose, so we might store it or we might slowly add the product of that decomposition to force that reaction in reverse so that we keep as much reactant around as possible. Now, the other change in concentration that we can do is to remove reactant or product. So if we're removing a reactant, the reaction will shift to replace whatever we removed. And so we take reactant away, we're going to shift to replace it so that we get more reactant being formed and products being used up. So the ways we can describe this, the equilibrium shifts left, or it shifts towards the reactants. The reaction proceeds in the reverse direction. On the other hand, if we remove product, the reaction is going to shift to replace the removed product, resulting in more product being formed and reactant being used. So the equilibrium shifts right towards products, the reaction proceeds in the reverse direction. So here in the case of removing something, the equilibrium is going to shift in the direction it needs to replace whatever we removed. So again, if I had A plus B producing C, if I were to remove A, we're going to shift to replace it. So it shifts towards A. So the consequence is that the concentration of A and B will increase. And we're going to use product. So C decreases. If I were to remove C, we're going to shift towards C to replace it. And so C's concentration goes up, A and B will go down. So again, in terms of trying to manipulate our reactions, if our goal is to create as much product as possible, we might set up a scenario where we slowly siphon product off as it gets formed. So we reach an equilibrium, and then we keep pushing it forward by removing those products in order to get as much product as possible from our starting reactants. So if we take a look at problem number 1, here we've got the reaction of carbon monoxide with water to produce carbon dioxide and hydrogen. We're asked what 2 things can be done to push the equilibrium to the right, so in that forward direction, to generate more carbon dioxide. So we think about the 2 manipulations we just talked about that are going to push the reaction forward. One would be we could add more reactant. Adding more reactant, we shift to remove what we add. We use reactants by shifting forward. So we can add more carbon monoxide or water. The other possibility that pushes it forward is to remove product. So we could remove carbon dioxide or hydrogen. So both of those scenarios would push that reaction in the forward direction, causing us to generate more product. So that's our first manipulation, is changing concentrations. We can either siphon product off over time, or we can add reactant over time if our goal is to push that reaction in the forward direction. Now, the next stress we'll take a look at are changes in pressure or volume. Pressure's primary impact is on Kp. So remember that when we are relating Kp and Kc, we had to worry about the change in gas moles. The same is true here. We've got to look at the number of moles of gaseous products versus gaseous reactants. It's only those substances that are going to be impacted by changes in pressure or volume. So if we find a scenario in which the moles of reactant are equal to the moles of product, then there's no change to our equilibrium. So an example would be if I had A plus B producing 2C. So my reactant moles, that's just my coefficient. So 1 plus 1 gives me 2 moles of reactants. My coefficient here gives me 2 moles of products. So those moles are equal. That would mean in this scenario, I could change my pressure, I could change my volume. It is not going to impact my equilibrium. Where we're going to get an impact is if the moles are not equal. So when they're not equal, an increase in pressure or a decrease in volume, remember from your gas laws that these are connected to one another, they're inversely proportional. If I increase pressure, my reaction is going to shift towards the side with fewer moles. So that's how we relieve pressure. So remember, we've got those relationships between moles and pressure. More moles have higher pressure, less moles have lower pressure. So if we're increasing our pressure, our equilibrium is going to shift to try to bring that pressure back down. And we do that by having less moles present. A decrease in pressure or an increase in volume will shift the reaction towards the side with a larger mole. So if we drop our pressure, the equilibrium is going to try to bring that, or the reaction is going to try to bring that pressure back up. And we get a higher pressure by having more moles present. So in either case, the shift occurs in order to relieve the pressure change, leading to a new equilibrium. So if we look at our example here, we've got nitrogen plus hydrogen producing ammonia. If we look at our gas moles on the reactant side, I've got 1 nitrogen, I've got the 3 hydrogen, so together that gives us 4 moles of gas. On my product side, I've got 2 moles of ammonia. They're unequal. Since they're unequal, a change in pressure or volume is going to shift my equilibrium. So here we have our reaction in a container where we can change the volume, which changes the pressure. So here if we push the piston down, causing a smaller volume results in higher pressure. My equilibrium is going to shift to reduce that increased pressure. So it's got to shift towards the side with fewer moles. My fewer moles here are on the product side. So here it shifts towards the product so that we get less moles present and it lowers our pressure back down. At the same time, if we were to increase volume, that decreases our pressure. If we decrease the pressure, we're going to try to bring that pressure back up with more moles. And so this time, the moles are on my product side. And so my reaction shifts towards the product. So with our pressure and volume, we've got to be careful because unlike adding or removing materials, it's not one set direction. So we always have to look at the moles. If we increase pressure, we want less moles, we shift to the side with less moles. If we decrease pressure, we want more moles, so we're going to shift to the side with more moles. So here we can look at another example. I've got A plus 2B producing C. If I look at my mole totals, I've got 1A, 2B, so 1 plus 2 gives me a total of 3 for my reactant moles. Then my coefficient for my C here is 1, so I have 1 for my product moles. So my reactant moles and my product moles are not equal. If I were to increase pressure, which is the same as decreasing volume. So increasing pressure, we always shift to the side with fewer moles. So in this scenario, the fewer moles will be the product side with 1. So this time it shifts forward. So that would result in the concentration of C increasing and the concentrations of A and B decreasing. But if I were to decrease pressure, which I can achieve by increasing volume, we're going to shift towards the side with more moles, again, so we can bring that pressure back up. So we're going to shift towards more moles, which in this case, the more moles is here on that reactant side, so it shifts in reverse. This would cause C to go down, A and B to go up. So for this particular reaction, again, if I want to maximize my yield, I could alter amounts of reactants or products. So I could add more A or B over time. I could remove C over time. Or because this is all gases, I could alter my pressure and volume. So here, if we were to increase pressure over time, we would cause our reaction to shift in the forward direction, getting more product. Now, our final stress for an equilibrium comes from changes in temperature. Now, the influence temperature has on equilibrium depends on the total energy change for a reaction. So delta E or delta H. So it depends on if the reaction is endothermic or exothermic. For exothermic reactions, remember that's where we've got a positive energy change. Delta H is positive. When delta H is positive, that is the result of the energy of the products being greater than the energy of the reactants. We end up with that higher energy state because we had an overall absorption of energy. That reaction requires energy. Since it requires energy, we can think of this energy as being like a reactant. It has to be there. We've got to add it or the reaction doesn't occur. So if we think about it that way, then increasing temperature is just like adding a reactant. And it causes the equilibrium to shift in the same manner. It causes the equilibrium to shift forward. So we shift away from when we add. We add energy, a reactant, we shift forward away from it, resulting in more products being formed and reactants decreasing. If we decrease temperature, that's just like removing a reactant. If we remove something, the equilibrium shifts to replace what we removed. So this would shift in the reverse direction, resulting in less products, more reactants. If my reaction is exothermic, remember we can indicate exothermic with a negative energy change. That negative value means that we have an overall lowering of our energy. And so we're in a scenario where the energy of our products is less than the energy of the reactants we started with. And this is because we get an overall release of energy. So exothermic, we are releasing energy. If we're releasing that energy, we are producing it as part of that reaction. So that energy can be thought of as a product here. And if we think of it as a product, then we have the same types of equilibrium shifts as if we were to add or remove a product. So increasing temperature is just like adding a product. It causes the equilibrium to shift in the reverse. We shift away from what we add. So it shifts in the reverse, getting more reactants, less products. So if I have an exothermic reaction, heating it is not going to be helpful. It's going to actually give me less product. If, on the other hand, I decrease my temperature, that's just like removing product. It causes the equilibrium to shift in the forward direction, resulting in products increasing and reactants decreasing. So with all of the stresses that we've talked about so far, we want to look at here is problem 2. We're going to use this Le Chatelier's principle. We want to explain how the yield of an endothermic reaction can be increased. So we want to describe all possibilities. So for any reaction, endothermic or exothermic, we can increase our yield, so increase the amount of our products, always by adding more reactants, we could slowly remove product. If we don't have a balanced equation here, but if our reactant moles and our product moles are not equal for any gases, if there's no gases, then there'll be no impact. But if there are gases and they are not equal, we could alter pressure or volume. And then in terms of being endothermic, so endothermic, that's that positive energy. We said energy is a reactant. We have to add it. So in an endothermic reaction, if we were to increase the temperature, that's adding more energy. That's the same impact as adding more reactant. It's going to shift our reaction forward. So for an endothermic reaction, a way to get our maximum yields, we would increase temperature slowly over time. We could add more product slowly over time. We could siphon, or we could add more reactant. We could siphon our product off. Now, the final thing to talk about is the impact of catalysts. Remember that the role of a catalyst is to provide a new mechanism with lower activation energy, resulting in an increased rate. The addition of a catalyst to a system at equilibrium will not change the equilibrium. It doesn't alter our concentrations. It's not going to cause any shifts. If we add the catalyst before equilibrium, we could get to equilibrium faster, but once we're there, it's not going to do anything. Now, the remainder of our worksheet, we've got some additional practice problems. We'll go over those practice problems in another video.